All right, so let's get rolling today. We said that the last three sessions would talk about investigation. The first two would be on so-called direct investigation. The first one we talked about was trenching and drilling, and we talked about the fact that if you want to drill a hole to get down to through the strata to be able to perhaps leave a hole to put instrumentation in, or to directly sample the strata, then you might trench or drill. If you're drilling, you need to use different methods if you're going through soil than if you're going through rock. Soil would be augering or using maybe rotary drilling with a tricone bit, but not taking samples as you go down. And rock drilling would be using a tricone bit, which doesn't take samples but takes cuttings at the surface, or a rotary drilling with a diamond drill, which does take samples, which we talked about last time. So now today we'll talk about how we might sample in a bit more detail in rock and soil, including the methods for sampling in soil that we didn't talk about in detail, how you might get the most benefit from your $10 or $50 a foot drill hole to make sure that you get the most information from it. In other words, putting instrumentation in it, which might be to measure water pressures and to do pump tests and measure permeabilities. And also perhaps actually only now, not now such a new method, but continuous profiling is methods by which you can just push a penetrometer directly into the ground and use the force that you have to push it with, along with the pore pressures that you develop at the tip of it, to be able to say something about what's in the subsurface without actually sampling it. And so we'll talk about each of these in turn. And we'll have some eye candy by looking at some materials. So talk about sampling in rock and soil. I suppose it might not be a complete waste to be able to just say the things that this one figure I'm thinking of from last time. And that is that if you're planning to drill, I guess I went past it, then the drilling methods fall into these three categories. Augering, to drive a corkscrew down through soil. No samples, just what comes up on the flights, which you can sample. Hollow stem allows you to sample down the middle through the methods that we'll talk about today. If you're drilling in soil or rock, then direct rotary drilling is one way to do that, usually with a tricone bit. Drilling fluid gets flushed down the center. It could be air. And the cuttings, which are broken off from the base of the hole, get flushed up to the surface. Maybe they hit you in the head, or maybe you just collect them to be able to see what you're going through at a given depth. And you know how many drill rods you have to be able to say how deep you will be and how deep those samples are coming from. And not cable tools, but the other method might be by diamond drilling, which is a cylindrical tube with industrial diamonds at the tip, the drill bit, which abrades the rock away. Fluid is circulated down the center where the core rises into the core barrel, is returned to the surface in the outer annulus between the drill and the open hole, or the drill and the casing, and the water is then reused when it comes back to the surface. And all that comes back to the surface is not drill cuttings, but actually just flour, basically rock flour, because it's being abraded at the tip. So that's what we talked about last time. We saw some photos of these different methods in action. So what do you do to sample? So this is actually in your notes. It's a column that goes from soil ultimately to rock, progressively harder soils, more granular soils, sands and gravels versus clays. And we did mention last time that the way that you sample these is fundamentally different from clays to things which are cohesionless, like sands and silts and gravels. And the main difference is that in clays you use what's referred to as a thin wall sampler. So it looks like this. It's maybe 1/10 of an inch thick wall of a 3-inch diameter brass tube which is coupled onto a coupling that goes down to the bottom of the borehole, and it's pushed in just like a cookie cutter. And as it's pushed in, the soil rises in it. You twist it to break it off at the base, and then you recover it. Because the holes are typically filled with water, then when you pull it out of the hole, there'll be a bunch of water above it in the drill pipe. And if you don't have a ball valve to stop the water pushing this out, it'll just wash the sample out. So that's what exists in the top. If it's really soft soil, then you have what's called a piston sampler. And that is that it has a piston which is on like a syringe almost, so that as you push it into the ground and this assemblage is pushed into the thin wall sampler, it moves up with the top of the sample, so that now when you break it off and pull it up the borehole, the suction that you have at the top of this actually keeps the sample in place. So if it's a silt that is water laden and would easily just wash out of the bottom, it tends to grab the sample. So for clays, they're always so-called thin tubes. They're always pushed into the bottom of the hole just by using the drill rod in the hole, putting a weight on it by the drill rig and putting it down, usually 18 inches or 2 feet, which is the length of this. Twist it, pull it out, and take it to the sample, to the surface, and receive it. In sands and gravels, you use what's called a thick-walled sampler or a split barrel. It's called a split barrel because it's a cylinder that splits in half. It's threaded at the bottom, threaded at the top, and screws into the top of the assembly here, and a shoe screws onto the base of it, and that's also put down in the bottom of the hole. But rather than being pushed in with a cookie cutter, it's actually hammered into the hole with a monkey hammer on a capstan, which we'll see later on. And as a result of that, the sample is a sand, and it's broken. It gets advanced up in the tube. It sits in here. This ball valve does the same thing as before. It stops it being washed out by the water that's in the drill stem as you pull it up, and you end up bringing this up to the surface as a disturbed sample. You break it off the drill string, you break the shoe off the base of it and the top off it, you split it open, and you take a disturbed sample in a bag with whatever fluids or denapples might be present in it as well. And so those are the basic two types of core barrels. These are just variants of them. So either thin wall for clays, maybe silts, and thick walls for sands and gravels. And in rocks, we talked about core barrels. And so core barrels has a diamond tip at the bottom, rotates, core goes up into it. And I guess we don't have more of those. So we'll look at some of those later in a moment. The various attributes there, I guess these are the same ones that we mentioned. So this is a split barrel. Maybe this is, maybe it's 2/10 of an inch, maybe less than 1/10 of an inch for a thin wall core barrel, pushed into the soil at the bottom of the hole, banged into the soil with monkey hammer, both with check valves to stop them being washed out of the sampler, a piston sampler where the piston follows it up to the top, and a rotary core barrel. We saw last time that there's an inner core barrel which is here. This assembly allows you to pull the whole thing up out of the hole without pulling all the drill stem to evacuate the hole, which takes a long time if you're down a couple of 100 feet. And this has diamonds studded at the tip, a core catcher at the bottom, which is like a comb, which is spring steel, which stops the core from dropping out and rather takes it up to the surface. And so those are the kind of things we're talking about. Actually, I don't know, perhaps it's worthwhile looking at these while we're here. So these are the things we looked at. Not sure how far we got last time. We talked about this core. This is the core you saw in a different setting from China's prospective radioactive waste experimental site, not necessary for waste, in the middle of the Gobi Desert, where they're drilling access to that. This is a drill rig in on the Arctic Circle, basically. These are a solid stem auger, multiple flights that have been pulled out of the hole with stuff on them, which you can pull off and sample, should you so wish. I'm not sure what's going on here. This is a core barrel that's being drilled into the hole. I think that's the same one, right? Yeah, just in a different circumstance. For drilling with water, it's not gas, it's actually hot water here, from a steam plant, because it is below freezing. So it's warm water that's used for flushing. So once you've used this, and if you don't recover it from circulating downhole and recovering it uphole, then you have to bring some more. Not a big problem at this particular site because it was close by. Not such great weather. And a solid stem auger. So male and female couplings for the auger with a clip going through it to join them. Drilled into the ground, brings up soil on the flights. You can sample at the surface. You can't sample from downhole unless you pull all the auger flights, leaving an open hole, and then sampling using if this is a clay, then you'd use a thin wall sampler, which it is, or if it's a sand, you'd use a thick wall sampler. And this actually is a core barrel. Actually, it's not. It looks a bit like a hollow stem auger, right, with a sampler going down the middle, but it's not. It's a CREL barrel, Cold Regions Research Engineering Lab. It's for sampling permafrost. So it's just a hollow tube, cutters on the base which you can't see, auger flights to ream the hole out larger than it is, but it's for going through ice in this particular location. And that's it coming out of the hole. Norman Wells, Northwest Territory. All right. So we talked about thin wall samplers. So this is exactly that. So this is a piston sampler. So this is a piston that's on a length that is now retracted into this housing. And so the idea is that onto this coupling here, you'd slide a very thin-walled sampler, which is this. So you perhaps can't see it really well. But this is a piece of brass tube. It's probably 1/10 of an inch thick. This is that piston that you just saw advanced to the end. This is at the bottom end of this tube. This coupling here is actually up here. And so you attach this tube onto this coupling by just unscrewing some bolts using an Allen screw. So they're recessed when you take it off. When you slide it on, you unscrew it so they come out into the holes that are on the top of this assembly here. So that attaches it. You place it on some drill string and you put it down to the bottom of the hole. Once it's down at the bottom of the hole, you then press this whole assembly into the bottom of the hole, and you allow this piston to naturally retract up inside as the bottom of the hole goes inside this thin wall sampler. And then once you have that, I don't know, this is it sampled. Whoops. This is with the sampler all the way up to the top. This is the thin wall. This is someone hitting the sampler with a hammer by the looks of it. This is the same picture as before. Yeah. So this has now been taken off the sampler. It's got a sample in it. So this is the piston. It's got 18 inches of clay included in it. If you want to, you can measure the strength of it with a Tor vane. I think there's a picture of a Tor vane. Tor vane is just a little wheel with these protrusions on it, almost like a mill wheel. You press that into the end of the thing with basically a torque wrench, something that you turn, and then when it reaches the limiting strength of the soil, it fails. And so the soil allows these mill wheels to rotate, and at that point you know what the maximum strength of the soil is just because of the torque that you've applied on the things. Torque is what, by definition? Do you remember that in your past life? What's the definition of a torque? Force times displacement. No, force times lever arm, right? Yeah, from 303. Cross products and all those things. So that's that. I'm not sure whether we shipped over stuff. So yeah, so this would all go down the hole on this drill stem. In this case, it's just drilling. I'm not sure what else we have in these figures. And to seal it, you seal it with paraffin wax. So this is just a can. This is a tiger torch. This is actually from the clothes people are wearing. It's in December in Boston, cold actually. And so you melt the paraffin wax, and then you seal the top of the sample and the bottom of the sample so that you seal in the moisture content and send it off to the lab. So this is where the sample attaches onto the coupling. So there'd be an Allen screw in here. You'd unscrew it to bring it out into the tube and therefore lock it onto the system. Cap it off with these things and then send it off to the lab, or keep it to do anything you want. So that's it coming out of the hole, I think, right? This is the brass tube. These are the Allen key holes that are brought out to attach it onto the piston sampler. The end of it. Taking out, removing those screws. Torque vane for measuring the strength. If you might not want to know the strength, but there are other applications in foundation engineering where that would be a typical thing to measure. Yeah, torque vane. So it just measures how much torque you apply before it finally gives, and it measures the remnant torque that it got up to just by, it's just like a dial on a watch strap. Yeah, all it is. Okay. I don't think I have any pictures. What else we're dealing with? Okay. Don't have any pictures, I don't think, of split spoons, but we will talk about what we do with split spoons. So the other thing that you do as you're sampling, if it's your first job, is you take a log of what's going on. So a drill log would record all the relevant information about what's going on. This is one for Golder Associates, which was WSP, the precursor to WSP, bought out by. And so typically things would be recording with depth as you go down from the methods of advance. So here in the left-hand corner, this is actually for Smithville. And the information here is the method of advance on the left-hand side. So auger, 150 millimeter diameter, hollow stem auger to get through the soil to some depth. And then from then on, drilling with a tricone to get down to the beginning of the rock. Then applying casing into it, maybe by widening the hole and putting casing. And then drilling through that casing with a rotary drill to be able to sample the rock. So within the soil, on the auger, you'd be able to sample it, and you'd be able to sample on the flights. And so you'd mark in the actual symbolic log, whatever you encountered, whether it was sand or silt or clay, and mark on the log exactly what it was. If you took samples by Shelby tube or by a split spoon, you'd mark those on there where you sampled. And then you'd also define what happens once you get into the rock. And in the rock, once you get below 7.5 meters, I guess in this case, not feet, you have a descriptive log of the core samples that you've taken by rotary coring. And so pretty straightforward and rudimentary. You provide also some other information. Everything's done with depth. You'd record whether you're taking samples in the soil. So it looks like no samples are taken in the soil here, but in the rock you've got rock core defined, and that would be boxed just like we saw on the core shed. And you'd also write down any information from the other soil samples that you might take. So we mentioned before that if you take samples in soil, they're either in clay, as in which you just push it into the ground under a constant force, or you take split spoon samples, which are for sands and gravels, which you bang into the ground. And so a standard test is you have a standard weight hammer which you drop onto it. It bangs the sampler into the ground, and you count the number of blows it takes to go a foot, 0.3 of a meter. And the more blows it takes to go a foot means the more dense and stronger it is, and sometimes that's used with empirical correlations for designing foundations, what kind of foundation you need for a house or a building or piers. Quite a bit rudimentary, but there's quite a database that's built up. And the other things that you might record would be how much recovery you get. So if you drill 5 feet and you recover only 2 feet of core, then you recover only 40% of the core. You might note how much of the core was solid versus broken. So the core you just saw from China was 3 meters length of core, which is 100% recovered and 100% solid. So probably a good place to have a waste repository because there's no fractures for water to flow in. The so-called rock quality designation, RQD, which is the percentage of pieces of core which are bigger than 4 inches, just as a measure of the quality of the rock. Again, not for groundwater hydrology, but for constructing tunnels to be able to evaluate strength. I can't read that. Fractures per meter is what that is. That would be useful for the things that we're doing here. Spacing of fractures would be 3 fractures per meter would be a fracture spacing of 0.33 meters. And if you also sample rock core and bring it to the surface, the orientation of the fractures that you have, which might be useful not so much for groundwater hydrology, but for designing things like rock slopes, where if you have steep fractures, they make the slope less stable. Whether you have surfaces on the fractures, which might be iron stained, indicating that there's active water flow, or whether you have calcite deposits, or whether you have slickened sides as release surfaces. And also, once you have these holes, you'd also define what kind of instrumentation you put in. And so we said before that in drilling this, you go down with a hollow stem auger and transfer to a rotary rig with a tricone to get down to rock. And then once you've got that, you place casing in the hole to stop the soil collapsing on you. And so the other information that you have is the completion within the hole, which is the right-hand side here. I guess I run out of page, which is saying what happens at each stage. So this has a casing going down. I guess this is one wall of the casing drawn in, the other wall of the casing going in. It goes down till you get to rock. It's grouted in place, so hydraulically it's sealed. And in this particular case, you have a standpipe piezometer. This tube down the middle, probably a 1-inch diameter piece of the plumbing that you have in your house, going down all the way into the aquifer to some depth. We'll talk about what they look like at depth, and being backfilled around that with sand to stop the borehole collapsing, and then being grouted in place to seal it. And so you can take water level measurements from this, and you can also conduct pump tests. So if in your GSci 452 class you talked about using slug tests or illusion tests, all it is that you fill up this pipe an extra foot from its static magnitude, you count how long it takes to go down to the resting water level, and you use that rate at which it declines as a measure of the permeability. The faster it goes down, the higher permeability, and you can calculate that pretty simply from some pretty straightforward closed form equations. So that way you're using your borehole, which might cost 10 to 50 bucks a foot, or 30 to 150 bucks a meter to be able to drill, because you're leaving some instrumentation in it which you could sample water from to see what's dissolved in water or what the free product is, and you can also use it to get water levels upstream and downstream if you want to calculate advective velocities, if you have permeabilities. And you can also see how concentrations would change over time, because you can recover stuff from it. So this column that I jumped over was hydraulic conductivity in, looks like centimeters per second, which is a measure of this. So if you measure those within the zone where this is open, which is down below the bottom of this, you could put the magnitudes of the permeability. So a pretty standard way of being able to make the most out of your wellbore, and it would not be an unusual thing to do for someone as an entry-level engineer working in a design office, consulting office. So that's that. So that's how to record things. I guess I had that as well. I have this, don't need to see me. Water sampling. I think we looked at this before. These are water meters, it's pretty straightforward. To measure water levels, if you have a piezometer tube, you can directly measure the water levels just by lowering this down into the hole. The idea is that this spool has a graduated tape. The tape on the left-hand side and the right-hand side has two conductors going down, which connected with a battery that goes in here and through a circuit with a light, or a ringer, perhaps it is, that you can turn on or off. And this, I guess if you have, perhaps you can see it. Yeah. See it? This is just one wire goes to the outer casing, the other wire goes to this probe in the interior. When you hit water at this level here, it makes a circuit, connects the circuit between this interior probe and the outer casing, and the light goes on. Did I switch pages perhaps or something? I jumped off here. So yeah, so you make a connection between these two, light goes off, you know how deep you are from the graduated tape, and you're able to say what depth the water level is. So pretty straightforward. More sophisticated ways of doing that are other ways of measuring pressures, are these piezometers. So one way would be to have this 1-inch PVC plumbing casing go down to a zone and then seal it in place. Another way would be have a tensiometer, which is a porous cube, if you like, or a porous filter that has two pipes going into it. And if this is measuring tension or negative pressure in the water in a soil, then you need to couple it to a manometer, which can measure negative pressures. Piezometers, in terms of water levels, can only measure positive pressures as a height above the datum, whatever that is. So a tensiometer would measure the suction in a soil, negative pressures, and it would use a manometer, probably not with mercury in it, but probably with water in it. And so-called electrical, pneumatic or electrical piezometers. So pneumatic piezometers would be a piezometer that has a membrane here, and the water pressure pushing up against that thin membrane. If the water pressure is high enough, it will push it up so it stops up against this area here. And if you try and force air down through this, then you won't be able to make a circuit to the return flow. If you provide an air pressure which you can measure at the surface, which is equal to the pressure acting here, then all of a sudden you'll have a continuous air circuit, recover air at the surface, and therefore you know that the pressure that you've applied here is exactly the same as the water pressure in your piezometer. So by definition, you know exactly what your pressure is. You can take water samples from this by either blowing water out through this stack or by using a bailer, like we talked about maybe a few classes ago. You can't take water samples in this because it's closed, nor this, water quality samples. And so electrical piezometers have also a membrane, but a little strain gauge which measures the displacement of this membrane. And so the higher the pressure here, the larger the displacement. And so if you measure the displacement of this strain gauge, you can calibrate it against the magnitude of the pressure that you're applying. So all of these are ways of instrumenting your borehole to be able to usefully get some information from it. You could run a permeability test in this piezometer. You can water sample from it for quality. You can also get water levels from this rudimentary sampler. You can't get water quality samples from any of these other three methods. Some exotic ways of being able to look at groundwater flow in rock, typically crystalline, low permeability rocks, is to be able to measure, have a thermistor which creates a temperature, and you measure the migration of that temperature along the borehole with a pulse. So if you heat the water here and it's flowing up the hole, then this thermocouple would measure an increase in temperature. This wouldn't, so you know which direction the flow is going. If you want to measure flow in direction, you could have something that samples temperatures across the cross-section of the hole to be able to have a heater in the middle. And if the left-hand sensors warm up, then you know that the flow is from left to right. And sometimes people use borehole cameras to be able to look at the rate at which particles are moving past the screen to be able to get a velocity that's occurring in the borehole. So you'd be interested to know if water is flowing in a borehole, because it would give you an idea that water is flowing into it, and therefore there's some permeability that's defined. And also you'd want to know that in terms of whether aquifers which are above and below you might be connected to each other. So anyway, so those are rudimentary piezometers. So in a single borehole, you might have multiple boreholes, multiple piezometers. And so the idea there is that at different levels, you might want in different strata to measure the permeabilities and or the pressures. And if there's nothing to separate those individual portions of your borehole, you'll only get a single hydrostatic curve within the hole. So if you want to separate them, you have to hydraulically separate them. So you run the tubing down to the base. You'd pack off the tubing with some sand around it, just like here, and then you'd put some grout down to be able to seal that packed off portion with a sand portion that's connected to the surface by one of these tubes. So it's just a piece of plumbing tube with some cuts in it to be able to make sure that it allows water into it. It's sealed with a lower seal of cement or clay, and then you move up the hole to the next segment. You then put down the next tube to the bottom. It's got some cuts in it to allow water into it. You backfill with sand, and then on top of that you either drop little pellets of bentonite, swelling clay, which are covered in varnish, which drop down here and then swell out to be able to seal it, or you grout it and then you repeat it all the way up. So this way, now you have a whole bunch of these individual piezometer, it's a piezometer nests. Each of these zones are isolated. You could run a slug test in each of these holes to measure permeabilities, and you can also sample the pressures at the surface by how far the water level rises in each of these by using one of those little probes, and you can measure it over time to be able to see what's going on in your system. And you can also sample water quality from each of these zones by flushing the hole or blowing it with nitrogen and then sampling back to the surface. So that's how you would put some instrumentation in your hole. So that's what that borehole log is alluding to, that below here you'd have a packed off zone at some depth which would be connected to the surface. In this case, it looks like only one piezometer, but in other cases, in wider holes, you might have multiples. And the other option, in a hole that you don't necessarily want to have a static piezometer installation, is to use a packer, straddle packer. So this would be a borehole in rock. This is a packer which is just the same white tube all the way up to the surface. But now at the base and above the base you have a packer. Packer is just a neoprene balloon which is placed on a mandrel. So a cylindrical mandrel with a neoprene tube around it, which is clipped both top and bottom. And so it forms potentially a sealed balloon, if you like. And then up to the surface, it's connected via these pipes to a nitrogen cylinder, gas cylinder, an air cylinder for that matter. Nitrogen's. Air is 90% nitrogen. And so you apply a pressure to be able to inflate this packer. It inflates against the side of the borehole. The upper packer inflates against the side of the borehole. So you have a zone here that's sealed. You can increase the pressure within this packed off zone by just raising the water level in this region here. You can check the water level above. When you do that, if this is leaking and not sealed, then it'll raise the water level here. If it's properly sealed, it won't. And you can run an inflow test or a pump test in this zone to be able to measure permeability and also measure the static water level if you leave it in long enough. And then once you've done that, you just drop the pressures, you deflate each of these, you move it 5 feet up the hole, and then you repeat it to be able to get potentially a profile of permeabilities all the way up the hole. So that when you filled your borehole log, you might have values for permeabilities in the rock portion, which might be a whole bunch of values as you go down here, just by doing that. So packers allow you to do that as you go down the hole. And that's about it. So what else do we have? Okay, let's look at some pictures, if we have any. What have we looked at? Actually, this. Actually, there were some straddle packer pictures. Where were they? Here's a whole bunch of underground labs. This is Mizunami in Japan, taking samples. Yeah, perhaps you might be interested to see all of these. It's a veritable tour around the world. We'll come back to that, perhaps. Yeah. I was looking for something. So the Korean nuclear waste program have an underground research lab where they have a whole bunch of instrumentation in Daejeon, which is just an hour high-speed train south of Seoul. This is Mizunami, which is the Japanese experimental lab for understanding the processes of migration of radionuclides around radioactive waste repositories. It's in granite, beautiful granite. It's unlined. And these boreholes are just instrumented with thin capillary tubes which go to zones where you can sample water quality samples from by withdrawing fluids, by sucking it out of these. Very sophisticated. You see a whole bunch of these sampling tubes going into the borehole and into packed off zones within the rock. This is taking a core at an underground research lab in the Swiss Jura, western Switzerland, a place called Monterrey, where it's drilled into clay shales. This is just a large diameter diamond drill, which is taking a sample out of the wall for testing. That's what the surface looks like in Saint-Ursanne in Switzerland. And the adits, where all of these experiments are run, lots of cores, lots of in situ experiments are run, borehole breakouts that indicate the stresses, people standing around looking at walls, Zurich. So experiments where they put heaters in the ground and they look at the migration of fluids because the heaters are representative of maybe hot radioactive waste canisters, which are placed into these clay shales, and you hope that the clay shales isolate the fluids so they don't travel very fast because they're low permeability, and they're also very sorptive, so they absorb radionuclides if you break those canisters. This is one of those tests, actually. This is actually just a model representation. It is underground. This is what the waste containers would look like. So a bunch of rods, radioactive rods in an assembly that are placed in a bentonite sheath. Now this is a container. This would be a metal container and then backfilled with bentonite around so that if this breaks open, you have low permeability, so not much water goes through here, and all of this, the radionuclides from this get absorbed in the bentonite. So that is. But this is a site where those experiments would be going on. Same site. This is actually the experiment. You can sit on here and pull yourself along 20 meters, I suppose, along this tunnel into where the experiment is, far away from the other tunnels. Who's that? Oh, could Mary Magdalene? Could be, yeah. St. Barbara, the patron saint of miners. Lots of mines have them. Just as the same that superstition was you can't have women in mines, underground. Bad luck. You do have women miners, certainly in the U.S., but that's what. This is an underground research lab in granite in Switzerland, Grimsel, in the base of an arch dam for the same kinds of things. A lot of sampling holes and some other things going on. A huge packer. So this is, we talked about packers, neoprene packers being inflated against a borehole. This is a borehole. It's actually a tunnel. This is a person's height. This is probably 6 feet tall. This is a ring that the neoprene is stretched against on the outside, with the idea that you can inflate it against the sides of this tunnel, and you can take water quality samples from the edge of it. So this whole length of this is going across a geological fault in this underground research lab. And the question is to look at what the characteristics of flow and transport are within this fault. And so one way to do that is hydraulically isolate the fault with a packer and do experiments that flow water along that. And I think you have people standing in it somewhere. So this is again the same underground research lab. This is what I was looking for. This is a neoprene packer. So this is the top and bottom. It has a straddle between them. It's not linked here. This is just a neoprene sleeve that's placed on top of a tube. It's anchored so it's sealed top and bottom, even though you can't seal it. And then these would be the nitrogen or air lines that inflate underneath here and push it against the borehole once it's been placed in the borehole. Yeah, so that's all it is. Not super sophisticated. More sampling. Cut marks from a TBM in a tunnel. A big calcite geode also in this, underneath this dam, with a viewing window that they put because This height here is the size of, this is 6 inches here, probably. Huge crystals. And on the surface. So there's the straddle packer. So this is a different place. So this is in a French former nuclear ballistic launch underground site where they had ballistic missiles, now decommissioned for running experiments. And this is a straddle packer. The upper packer, the lower packer, the straddle zone where you measure fluid pressures or inject fluids, the small line that links the upper packer to the lower packer for the air tank, and then this whole assembly is introduced in the borehole and then isolates the upper and lower zone where you can do these experiments. Yeah, the doors, heavy doors within this. Again, Switzerland. And doing experiments in a borehole in the bottom of one of these things. Yeah, that's the end. So that was, I guess that was what I was looking for. I was looking for the straddle packer. The last thing to chat about as we go through this is we mentioned direct push imaging. So one way to image in the subsurface but never take a sample is just to push a probe into the ground and try and use that probe to measure what's going on in the subsurface. So this is called cone penetrometer testing, which is here. And this is a not very good picture of the inside of a cone truck, so inside one of these trucks. And so the idea is that you have a 10 centimeter cross-sectional diameter solid steel rod, which has a conical tip on it. It looks like this. And that is pushed through the bottom of this truck when you're sitting inside it in here. Whoops, didn't mean to do that. And it's done by gripping onto this rod, which has this cone out of the bottom of the truck, which looks like this. And you merely use this turntable to advance down at 2 centimeters a second, and you measure at the tip of this probe the force that's applied against this cone, the force that's applied on the sleeve of the cone, so you can take these two forces away from each other and figure out which one of these is kind of friction on the side of the cone and which one is end bearing against it pushing down. And you also measure pore pressure in a porous frit, which is right behind the tip, which is generated by pushing this to the ground. So the basic idea is that coming out of the bottom of this truck, you can measure a profile with depth, which is the resistance of this tip as you go down, so-called tip resistance, the friction that's applied on the side of this sleeve, and also the pore pressure that's generated at this tip. And so if you look at any particular depth, then you have magnitudes of each of these three parameters: the tip resistance, the sleeve friction, and the pore pressure. And you can use empirical correlations that allow you to take the end bearing of the cone, which you can measure at any particular depth, how much friction you have on the side, and it gives you a location on one of these charts. And you can use that to define a zone which might say something about different magnitudes of permeability, either from empirical information where you have other people measured permeability where these two metrics were the same and are corresponding to these particular zones, or you can actually use methods to be able to reduce the magnitude of the pore pressure based on how high it is. If you imagine that the pore pressure here is due to the fact that you're pushing in basically an inch diameter of solid steel into the soil, you're displacing the soil, and so you're compacting the soil that you're displacing. And if you imagine compacting the soil that you're displacing, it has less pore volume to sit in, so you'd imagine that pore pressures would go up. So you're loading the pore pressure of the soil by pushing this in. If you had a really permeable soil, you'd imagine that the pore pressures would dissipate instantly to background. So that would be indicative of a high permeability material that you're going through. And if the pore pressures that you're going through stay high as you're advancing this, then you'd expect that to be indicative of a low permeability material. So there are methods of being able to take the magnitudes of those pressures to be able to say something about the actual numerical magnitude of the permeability. And so these look like this. If we go back through this, if I can find it, this. So this is exactly.
Oh, that's the movie again.
So this is a geoprobe tester. It's a vertical arranged guide with a mandrel on a turntable on top of it. It doesn't turn, but it pushes down. It takes these roughly 1-inch diameter pieces of, look like they're about a meter long, through which you thread cable to the tip of the cone, and then you assemble them here and then be able to run them at constant penetration velocity of 2 centimeters a second, and you record the end bearing pressure, the sleeve friction, and the pore pressure of the tip, and record it digitally through this cable. So this is, see if it comes up. Where in the world is Carmen Sandiego, do you think? California? So this is, it's just east of Istanbul, a place called Sakarya. The Izmit earthquake, maybe 99, I can't remember when. This was later than that. This is 2010, I think. But they had an earthquake there where big loss of life was by buildings collapsing because of liquefied foundations. And so this was basically looking at the foundations. You can use this to look at the liquefaction susceptibility of sands in an earthquake to be able to design mitigation methods. So this is the geoprobe. It's on a little nod well. You can drive it into buildings. A stage goes up and down along these guides at constant rate to be able to push this in. This is the cone at the tip. This is the end bearing. There's a load cell behind this. There's a load cell behind this that measures sleeve friction. There's a porous frit here that allows you to measure pressures in the pore pressures outside here. You need to keep it saturated before it goes in the ground, so you saturate this porous frit with some silica gel. Do you know what the sheath is that's on this? No? Well, it's a condom. Okay, fine. So this is a condom that's put on here to be able to saturate the frit here with silicon oil. It's usually boiled in silicon oil to be able to get air out of this solution, so that when you put it into the ground, it's fully saturated with no air in it, which affects the pressures that you measure. And then you place this into the ground. We've got a longer one somewhere. Yeah, so you see it pretty well. So you stack up these rods here. You have the tip on the ground. You get it pushed into the ground by this stage going down. And once it reaches the bottom, you've already added another rod on top. It's just screwed on because you have them on this sequence here. And then that's pushed into the ground. As it's going into the ground, you add another meter. And then once it reaches the bottom of its travel, you immediately go up to the top and clamp it and continue. And so I think we've got some pictures of it doing that here. Always be self-aware if you're on camera. So you see this pushing it down. It's going down at 2 centimeters a second. Oh, you'd like to see that again, wouldn't you? No? Going down at 2 centimeters a second. You just add another rod on here once it's at a convenient height. They come out, I guess they're all threaded on the ground, and then you take the digitally acquire pressures, tip resistance, and end bearing, and then use that to say something about the subsurface. For your interest, it would be permeability distributions with depth, but you can also use the other metrics to be able to say something like whether it's a clay or a sand or a silt. And obviously you can't use it in rock. We looked at all these. So what else was I going to talk about? That's Turkey. I guess I had a couple of things here. Well, to go on with this, this is also the same deal. This is a site in Delaware on actually a petroleum refinery. The same kind of deal, but it's mounted on a big truck. And you can see this is the gantry. Yeah, this is exactly the same as we saw before. So this is the cone below. It's wrapped in a piece of bicycle inner tube here to be able to keep the frit saturated before it's pushed into the ground. If we speed it up, once it goes into the ground, it just rips that frit off. This happened to be a so-called VIS CPT, as in VIS, as in visual. And so it's an interesting idea in that as it goes into the ground, it has a TV, it has at the tip, it has a CCD and a sapphire screen like you have on your watch to be able to look out into the soil that you go past. And so it records the grain size and the presence of DNAPLs in the soil as it goes down with depth. And so a bit of an exotic tool, kind of an experimental tool. I don't know whether people use them in practice, but it was using that to be able to do that. And just the yeah, I don't know what this is. Yeah, so going into the ground, you can't see much more than that. I know I'm moving. Yeah, okay, that's it. Yeah. So this is the tip of the pressure measuring element, end bearing. It measures the load that's applied on this sleeve. It has this portion, if I wind it back. Perhaps you can't see it so well. This here has a little window in the side, so it measures the grain size roughly a meter behind the tip is, but you know where both are. You know that you'll finally get there once you get this window to go down to where the tip was, and then you can record that continuously as it goes down. So kind of an interesting way of doing it. This is the end rod that it gets added to as it's pushed into the ground. I'm not sure whether we see anything else here. With a colleague from the university group out of the University of Michigan who owned this truck. Yeah, a bunch of other stuff you don't probably interested to see. And finally, going back to this, to see stuff in action. You saw the photographs from this before, but this is exactly that same site somewhere in Boston. This is the borehole with stuff in it. I'm going to go through. It said 12 minutes in my notes. I don't know. It was actually to do, actually this is what it wasn't. The whole purpose of this project was to look at a probe, which is basically a pencil that goes on the end of a penetrometer. This is to go down an oil well in the Gulf of America to be able to record the pore pressure at the end of this tip away from the bottom of the borehole. So the bottom of the borehole, which this goes into, would have the seabed pressure in it, and you want to measure the pressure actually in the formation. And so to do this, you wanted to see whether we could do that. I tagged along on this project. And so this was just to deploy this onshore in 15 feet underground to be able to see if it would work or not. So this whole site investigation project was to do that. So this was the drill rig that was mobilized to be able to do this. And so we don't really need to that, but so this you've seen before. This is the drill still going into the ground, water circulated along its length and then returned out of this T-bend into the bucket, into the bath, as you see going there. And then the supply of the water to the hole is sucked back out of this bath. You can see a couple of things on here which are to isolate the end of the bath to stop the cuttings going down to the end and be able to have clean water that you recirculate. So this is the drill going down, water going down inside the drill sting from this supply pipe. A turntable and a universal joint goes down to the bottom of the hole, brings up the cuttings. So this would be circulating water, maybe with drill mud, but also with cuttings in it. And so you might put a sieve across here to be able to sample the cuttings, to be able to see what you're going through. Pretty rudimentary. So that's kind of drilling. Don't know what else. Yeah, we talked about sealing things by putting some twine around it to be able to seal the joints so you don't lose water. So any fluid that you pass down the center of the drill stem goes down instead of just squirting out to the side. So pretty straightforward. Adding drill string. So pulling stuff out of the hole in this particular case. If I put it on fast forward. Tricone bit going down the hole. I think a sampling tube, I don't know. There you go, that's what I wanted. So we talked about the different samplers, the Shelby tube, which was a thin-walled sampler, which was deployed on this site, but it might be actually banging in a Shelby tube. I think it was actually, rather than the split spoon sampler where you bang it in under a given weight, I guess. If I wind this back. So there's a sampler down at the bottom of this hole that's been introduced. The drill bit has come out of the hole. A sampler has been entered into the hole at some stage. I can't quite get it. I think here. This is the monkey hammer, which is just a big heavy weight with a thinner piece of pipe in the bottom of it that ultimately is screwed into here. The hammer is lifted up into the mast by wrapping a coil around this capstan here. When you tighten it, it pulls it up into the mast. You loosen it, it drops, etc. Very straightforward. You only have to see it once to know exactly how it works. Getting some samples out here. I'm not sure. I guess that's that. So you see exactly that. So you tighten on this. You're not pulling up this weight, which is much heavier than you do with this amount of effort. You just tighten it on the capstan, and the capstan provides the motive effort. You measure how many blows it takes to go down a foot. You record it, and then you recover the sample, which I guess they're going to do with this. I think we're still running on fast speed. I'm impatient. Still doing it. Still doing it. And I think it was a thin wall sampler, and I think it crimped the toe of it. So very straightforward. So this is the drilling equipment, which is moved out to the side with the turntable and the water pipe that goes down to the base. Not sure what we're taking a picture of there. Keeping on doing it. Don't know why it goes dark. And then you withdraw the sample. Pull up the drill pipe. Perhaps that's putting it back again. You'd pull up each length of pipe, you'd clamp it at the bottom so it can't fall down the hole. You unscrew it, and then you lift it off in the mast, and then you bring the coupling down to the base, you tie it on, and then you lift up the next piece of drill pipe into the mast. You clamp it off at the bottom so it can't fall down, you unscrew it. So that's why you don't want to pull 100 feet of drill stem, because it's quite laborious. So this is the piston sampler, the pictures that you saw already. This is the Shelby tube that's already added onto it. I guess Shelby is someone's name. Ready to be deployed in this particular case. Don't know what happens now. And this is it being deployed, I guess. So lift it up into the mast. Don't know why that bit goes so high. Measure how deep the hole is with a tape measure. That's all that's being done there. And I guess that is getting ready to maybe deploy this Shelby tube. These are the Allen keys that bring the bolts out to be able to attach it to the piston sampler. And then I'm guessing that probably it might go down the hole. Yeah, it is going to go down the hole. Oh. Unfreezing stuff. I thought I saw someone, like me perhaps, trying to uncouple it. Whoops, whoops. Yeah. So these are just these Allen keys. So you use Allen key to take it off. You screw the Allen key into it so it's flush with the, it goes below the Shelby tube, and then you can lift the assembly off. Not sure if there's anything else left on there. Working in wintertime, have to unfreeze things. And these are just the end samples. Not sure what else is done here. Yeah, so actually you can see it's crimped. So it was circular in the section, now it's been pushed into a rock by banging it into the ground. Must have been hard clay, and that's why we did it, I'm guessing. I think that's probably the end. Good. The end. Fascinating, huh? Good. So we've talked about, I won't look at that anymore. We've talked about 2 out of 3 things we want to talk about. So the first was how to drill holes in soil and rock, and the different methods. How to get the best bang for buck from those holes by sampling from them and also instrumenting them once you have them there to be able to get the best value. And the third will be to, now that we know what might be in place along a very thin slither, which is the trajectory of the borehole, but probably only a few inches either side of it if we have samples, how do you get to see the picture of the whole site, which might have 10 boreholes that are separated by tens or 100 meters? How do you fill in across the site? Well, the way to do that is to use geophysics. And so we'll talk next time about how we can infer what's in the rest of the site by using geophysical signals of seismic velocity, electrical resistivity, radar, to be able to actually create a picture of the site between the boreholes, and then use the boreholes to calibrate it against places where you know exactly what is in place. And so if you know what the geophysical signals are at those locations, you can ground truth your boreholes against your predictions from the geophysics. So that's what we're talking about. And that will be, sadly, I know, your last class.